Okay, so welcome everyone to the second Australian session of RQI-Online. So our talks today are sort of broadly in the field of gravitational induced decoherence and ways of measuring it. Our first speaker this morning is Harshit Verma from University of Queensland. So Harshit, do you want to try sharing your screen?
Yeah, just a sec. Yep.
Fantastic. Well, I can see that and I can hear you nice and clearly. So let's get started. So as I said, Harshit is from University of Queensland and he's going to talk about the effect of environment on the interferometry of clocks. If I can get that out. Okay, thank you.
Hello, everyone, and good morning to everyone in Australia. I guess it's evening in Canada. So thank you, organizers, for allowing me to speak. This is my first talk in RQI, and this is a subject that I've talked about in before, but this is a newer version in the sense that we have some extra results. And the topic is effect of environment on the interferometry of clocks, which has been done in conjugation with my PhD advisors, Dr. Zich and Dr. Costa, here in EQUAS at University of Queensland. So before we move forward, I would just give a brief overview of the talk. So firstly, I will delve a bit into a historical perspective and the motivation of pursuing this particular project, and then go on to define in the second part of my talk the theoretical framework that is going to be what are clocks and what kind of systems do we consider as clocks, what kind of interferometry are we referring to, what are the main parts of the interferometer, and then go on, finally talk about the environment, the noise model, and how do we discuss the effects of environment in such a system. Finally, we will get some analytical. We'll discuss some analytical results and the qualitative aspects using plots in various noise models. For example, the Jaynes Cummings and channel-based noise models such as the amplitude damping model, phase damping model, and depolarizing model, and perform a comparative analysis. We'll see some intuitive regimes where one can intuitively expect the plots to follow some line of thought. And finally, we will try to figure out some figure of merit for future experiments. May not be ideal in the sense that the technology is not yet there, but we'll try to bring in different results from different experiments, the best results from different experiments, and arrive at a set of parameters which one could expect in future experiments, and what effect would noise have on those results. And then I'll go on to summarize my talk once again. So the first, the historical perspective that is there, this project takes with it is the interplay between quantum mechanics and gravity. I guess most of us are already familiar, but just for the sake of reference, I'll try to give out the assumptions. The assumption that we make here is the low energy limit, where the formalisms of quantum mechanics and gravity are held to be valid without any major modifications. And the first proposal in probing this interplay between quantum mechanics and gravity was the COW proposal, which is neutron interferometry, and the gravitational potential difference, which gives rise to measurable phase, though this effect is not just confined to gravitational potential difference. In general, it could be for other kinds of potential differences. So this gives rise to a measurable phase between paths of a neutron, which is prepared in a spatial superposition. And the gravity that is considered here is merely Newtonian, in the sense that there's no discussion about time dilation or relativistic effects. The proposal is very simple in the sense that you say, just a second, get a pointer. Yep. You see a neutrino is prepared in spatial superposition by a beam splitter, and as it goes through two different paths having two different gravitational potentials along them, it accumulates a phase, which can be measured by using a phase shifter on one of the paths. So the contemporary proposals in this regard are based on two broad themes. One of the major themes is what are the gravitational effects on quantum systems. In that, the paper that I'm going to follow is going to be the 2011 paper, which talks about interferometric visibility as a witness of GR proper time. And the second line of thought, or the second kind of proposals, have been broadly based on studying gravity as a quantum force or of quantum nature. That is, can gravity as a locally acting force lead to entanglement between distant quantum objects? So for probing gravitational effects in quantum systems, we are going to resort to the formalism of clocks. So the clocks that we consider here are merely systems with some internal degrees of freedom, some internal structure. And the proposal here is to study time dilation. So what clocks are not here are not perfectly time-keeping or time-emulating machines. That is, they do not necessarily have a mechanism to give out the information of what time they're measuring or how precisely are they measuring the time. The physical systems that one can imagine of having such qualities, for example, the simplest could be the energy levels of an atom or the vibration levels of a molecule. How does a clock work? A simple clock that we are referring to works by time evolving according to the proper time. So you initialize the clock into some state which is not the eigenstate of the clock Hamiltonian. You time evolve it, and the time evolved state depends on the proper time tau. So we have put a label tau on the time evolved state, which evolves according to proper time tau, and the internal Hamiltonian of the clock h int. So how can these clocks be used to study gravitational time dilation, or in what kind of experiment do we see the effect of time dilation using such clocks? Is that of a simple Mach-Zehnder kind of setup. Without going into experimental details, one can easily describe it. M1 and M2 here are mirrors. BS1 and BS2 are beam splitters, and PS is the phase shifter. D1 and D2 are detectors. So paths gamma 1 and gamma 2 have proper time difference between them. That is to say that they have gravitational potential difference between them as well. But on top of that, talking relativistically, they have certain proper times associated with the paths, which are different from the lab time. So you initialize the clock to a non-eigenstate, and then as it goes to the first beam splitter, is prepared in a spatial superposition, and that spatial superposition is given by the path degree of freedom. And here 1 and 2 refer to the path degree of freedom. Just before detection, one can write the state of the complete system as an entangled state between the path degree of freedom, here given by 1 and 2, and the time evolved states of the clock as it traverses paths gamma 1 and gamma 2 respectively. So there is an entangled state. That is an entangled state between the path degree of freedom and the internal degree of freedom here. If we calculate the detection probabilities on detectors D1 and D2, we get this sort of expression, which depends on the absolute value of the inner product between the time evolved states tau 1 and tau 2. Tau 1, for example, corresponds to the path gamma 1, and tau 2 to the path gamma 2. Using this, if we calculate the visibility, we get visibility is just the absolute value of the inner product between the time evolved states. And what we see here is that the visibility could be less than 1. So for example, if we were not to keep track of proper times, then this effect would not arise, and you would get a uniform visibility of 1, which happens, for example, in a COW type experiment. But if one keeps track of proper time, the visibility will be less than 1. So where is the role of gravity in all of this? In general, you could have arbitrary gravitational gradient or potential that could induce, which could also mean that you have different proper times, which are arbitrary. But in general, in specific case, you could have this proper time difference as a function of the separation between the paths of the interferometer. and the gravitational acceleration constant, for example, if you are on Earth, and the lab time, which is t. So because of the complementary relation between the distinguishability of the paths, that is which path information, and the visibility, you see a drop in visibility when you have more distinguishable paths. So these clocks carry information of the paths, and which leads to a drop in visibility. In general, in terms of clocks, the visibility is nothing but the expectation value of this time evolution operator, which is the usual time evolution operator, but the time factor here is delta tau, which is the proper time difference, tau1 minus tau2. So why should we consider noise in such a case? So I think it will be clear after we discuss bit. For example, there are numerous experiments that have been performed in which more massive particles and have been prepared at much larger distances than what is required for such kind of experiments, or probably would be required for such kind of experiments. But this does not happen in isolation. So the focus in most of these experiments is on the external degree of freedom, that is how to prepare the part degrees of freedom in a spatial superposition, and therefore there is a trade-off, or there is a disregard for the internal degrees of freedom, which, as I motivated before, could be the single most important factor for getting a drop in visibility, is the single most important factor to get a drop in visibility. So what kind of noises can one theoretically consider in a Mach-Zehnder setup without going into experimental details? One could have, for example, noise on the part degree of freedom, which leads to a dephasing of the superposition. The answer in that case is quite clear, that the number of particles reaching the detector would be lesser, and there would be a loss in visibility because it's no more coherent, I guess. So the superposition is not that coherent. The second case which my focus will be on is the noise on internal degree of freedom, that is on the clock. And in that, one can have two cases. One is that the noise on internal degree of freedom in itself is dependent on path, which means that some which path information is carried just because of the fact that the noise is dependent on path, which leads to a complex behavior. In the other case, a more simpler case, which we will primarily follow, is the path independent noise. That is, there is no difference between noise models to be considered on both of the paths. The noise parameters will remain same. However, the noise Hamiltonian, as we see later, will be also redshifted, as will be the clock Hamiltonian. So this could lead to a loss in which path information, as noise corrupts the which path information, and as we saw with the uh, complementarity principle before, that this would lead to a gain in visibility. If we consider these noisy clocks to be having additional degrees of freedom which interact with the main clock, in that case, you would have a big clock, that is additional degrees of freedom in the clock, and this would lead to a loss in visibility. I would explain this later as we go into noise models. So what are the some of the experimental realizations? We just discussed a few theoretical motivations for, or the framework in which we can consider noises. In experimental literature, one can see that there are various Mach-Zehnder interferometers which have an optical, framework in which the main kind of noise sources discussed are photon loss, short noise, and channel-based noise, theoretically mostly. And then atom interferometers could have vibration noises, and they are susceptible to stray magnetic fields and gravity gradients, etc. Now, mostly when we talk about experimental sources or experimental papers, what we see is that these noises are discussed in the context of phase estimation protocols, which, for example, could include tests of GR and detection of gravitational waves, etc. And there is no reference on internal degree of freedom in the phase estimation mostly, except during atom interferometers when you have to use them to impart or reduce the momentum of for use in interference. So For visibility experiments, one cannot just disregard the internal degree of freedom at all. One needs to consider them, as I said before. And uh, that leads to the answer that quantum noise could affect the internal degree of freedom, and hence, because of its evolution through a noisy environment, one would see some effect on the visibility. So how does one model the noise on internal degree of freedom? Is by considering extra quantum degrees of freedom, which are interacting with the clock. These we call as environment degrees of freedom. The final internal Hamiltonian, which will correspond to the clock plus the environment, would then be the intrinsic Hamiltonian of the clock plus the noise Hamiltonian, and add to it the environment Hamiltonian. In this framework, there are two implications that one could arrive at. One is that large Hilbert space of the clock and the environment could lead to a better timekeeping and hence further loss in visibility. And the second is that because of corruption of each path information, there could be an increase in the visibility. So as I said before, there's a complementary relation between distinguishability and visibility, which is highlighted here. And therefore, the kind of picture that we get is after the particle goes through a particle beam splitter, it experiences noise on its internal degrees of freedom. So how does one arrive at the expression for visibility in the case where noise is acting or you have environment acting on the path on the internal degree of freedom as it traverses through the paths of the Mach sender, is by considering the internal Hamiltonian now to be the sum of these Hamiltonians and the time evolved states to also reflect the complete time evolved state of the clock as well as the environment. So the visibility now will be having the same form, but the system now is clock plus environment degrees of freedom. So the first result that I would like to highlight here is the Jaynes Cummings model for which we have considered the single field approximation. And at zero temperature, what does it lead to is you have a simple Hamiltonian, which consists of a sigma z type, like the clock Hamiltonian, delta E times sigma z. The environment Hamiltonian, which has a frequency omega k, and a noise Hamiltonian, which depends on the noise parameter lambda, and simply leads to either a decay of the clock in excited state or excitation of the clock in the ground state. The initial state of the bath, as we are talking at zero temperature, would be the ground state 0. And the visibility can clearly be calculated using analytical tools very simply, which is found to depend on the noise factor and the difference in the energy level of the clock and the environment Hamiltonian. So firstly, what we see here is how does this visibility get affected by the clock Hamiltonian, given here, represented here by the energy of the clock Hamiltonian delta E and the energy of the noise Hamiltonian lambda. For proper time difference, delta tau is equals to 1, and for fixed omega k, we see that we can have regions of higher and lower visibilities than one would expect without the noise in general, and which is very interesting in its own right. But this also gives us a clue about if you're performing an experiment and you have certain internal Hamiltonian, and depending on the detuning, you can calculate in which region you would be, and therefore what kind of results to expect. Not necessarily that the visibility will be uniform because of noise. The other factor that this visibility depends on, of course, is the environment Hamiltonian, in this case represented by omega k. And we see that in the low noise regime here given by lambda, the visibility is a function of omega k, and in general one sees that as omega k is increased, the visibility is low for lower values of the noise parameter. Now one can ascertain certain thermal effects also by considering the Jaynes Cummings model. What kind of thermal effects? Well, one can say that the initial state of the bath is no more a pure state, but a mixed state. And then the visibility for such mixed clocks, that is the clock plus the environment, which is again a mixed state, can be calculated by this formula, which was highlighted in previous literature. So the factors P beta here represent the weighted contributions of the Boltzmann distribution. So represent the Boltzmann distribution in that sense. Again, one can do some analytical analysis and obtain the visibility as a function of all these parameters, and of course of the temperature, as I will show later. So what one sees here again is the interplay between delta E and lambda, which one can calculate simply. The interesting effect one sees here is also of the temperature. So depending on P betas, where beta is the inverse temperature, one sees that the visibility is in general lower for higher temperatures than for, let's say, T is equals to 1, comparing with T is equal to 10. So for a fixed parameter delta tau, we see that the high visibility features of this plot are lost as one goes into high temperature regime. We will see how does this compare with other parameters. Right now we are seeing it, how does it compare with lambda, and we see in the low lambda regime, one can clearly say that for high temperatures, the visibility is much lower than at lower temperatures. Now we move on to channel-based noise models. I still have, I guess, 10 minutes. So for channel-based noise models, we consider environment degrees of freedom and a minimal number of environment degrees of freedom, which one can use for noise modeling, as I will show with example. The main steps that we follow here are that we know the interactions that happen in such noise models. That is, we know the unitary time evolution operator, which governs the evolution of the clock, or sorry, which corresponds to the noisy evolution of because of these interactions. We perform an eigendecomposition and obtain the corresponding Hamiltonian, which just corresponds to the noisy dynamics. Add it to the intrinsic time evolution, intrinsic Hamiltonian of the clock to get H int, which is sum of these two. The assumption that we make here is that the environment does not have an evolution of its own. So through H-int, we again perform an eigendecomposition, and we get U-int, which corresponds to H-int. Now U-int would correspond to tau1, would have these factors tau1 and tau2, depending on which path you are going to gamma1 and gamma2. So tau star here was some intrinsic time scale associated with the dynamics of the noise model. And tau1 and tau2, after all these steps, would correspond to the actual proper times along the paths. You plug in the initial state in this U-int, and you get the final state, and then you plug in the final states in the visibility expression to obtain the visibility. So for example, for amplitude damping channel-based noise model, the interaction that one could consider here or are physically motivated is that of de-excitation of an atom, or the excitation of an atom in a ground state, with one more degree of freedom, here a quantum degree of freedom, which corresponds to, so if the atom is in excited state, there is a chance that it could well be remaining in the excited state while the extra degree of freedom is also in the ground state, or it could lead to a flipping where the environment degree of freedom flips to an excited state and the atom decays to the ground state. So such channels can be written, the effect of such channels can be ascertained by a unitary transformation, which intrinsically contains this term tau star, which is the time associated with these probabilistic processes happening, the time scale of these processes. And by making substitutions and eigendecomposition, one can, as I told before, one can obtain the Hamiltonian corresponding to the amplitude damping channel, add it to the intrinsic clock Hamiltonian, and get H-int. Now, after H-int, we go through the process of obtaining the time evolved state and finally obtaining the visibility. So again, what we have described or shown here is, sorry, the interplay between the clock Hamiltonian represented by delta E and the noise Hamiltonian represented by lambda. We see that as the proper time difference is increased, some peculiar features of high and low visibility what we call as fringes can be observed in the visibility pattern. Now here it is assumed that the noise is not path dependent. That is, it has the same lambda on both of the paths. Lambda1 is equal to lambda2 is equal to lambda. But a more interesting or a complex behavior case, as I said, told before, could be when you have path dependent noise, in which the probabilities of these transitions are not same in both of the paths. And the interesting thing that we see here is that even for proper time difference of 0, where you would expect maximum visibility 1, we see that there is a difference, or the visibility falls if the probabilities are not equal. So, and further, for higher proper time differences also, this the plot is, or the visibilities are qualitatively and quantitatively different from that you would expect from non path based noise models. So this is an interesting case, but this may not be entirely very practical. We expect that you have different noise or different environment interaction strengths along the paths. But of course, it is interesting. Now we can do similar analytical calculations for the phase damping channel and the depolarizing channel. The main difference being here is that the kind of interactions that are considered are of course different, and also the fact that the minimal dimension of the environment that you require for modeling the effect of modeling the effect of channel. So the dilation of the channel requires minimal dimensional environment, and that is 3 in case of phase damping channel, 3-dimensional environment. It was 2-dimensional, or sorry, it was 1-dimensional or single qubit in, it was 2-dimensional in case of amplitude damping case. This one has 3-dimensional environment, and the repolarizing channel requires a minimum of 4-dimensional environment. So we see that qualitatively all these plots are different, and of course the analytical calculations are also different. And this again leads to formation of fringes as the proper time is increased, but the visibility of 0 can also be expected for a finite proper time difference, which is not intuitive. And the kind of drops or the kind of patterns that you get in the interplay between clock Hamiltonian and the noise Hamiltonian is different for all these channels. Of course, these all discussions are in the case where lambda1 is equals to lambda2 is equals to lambda. So finally, coming to the comparison between channels, we can see that because of the difference in dimensionality of the environment, we see in the low noise regime, the visibility drop in the depolarizing channel is most in the channel-based noise models, and is followed by the phase damping channel and the amplitude damping channel. As I said before, there's a trade-off between rich path information and the dimensionality of the system. So as the dimensionality increases of this clock system, so the clock is clock plus the environment, you see a higher drop in visibility than you would expect for, let's say, a lower dimensional environment-based system, for example, the amplitude damping. So the Jaynes Cummings is different from all of these in the sense that it is not devoid of H environment. That is, H environment is not 0, and we see that for different temperatures, and one can ascertain the trend that at higher temperatures the visibility is much lower for Jaynes Cummings based noise models. And so the main points are given here that even at lambda is equals to 0, visibility falls further for Jaynes Cummings model. And that is just because of the fact that even though there is no coupling to environment, the environment is also self-evolving. So that was the plot for visibility versus the noise parameter. Here we have plotted visibility as a function of proper time difference delta tau while keeping delta E constant. On the right panel, we have plotted visibility as a function of difference in energy levels of the clock as a function of while keeping delta tau fixed. So what happens here is we see that for channel-based noise models, which are D, E, and F, the blue lines represent non-noise evolutions of the clock, and there are significant deviations as the noise parameter increases. Again, in the low noise regime, that is for small proper time difference, one can see that depending on these noise parameters, noise parameter lambda, there is a fall in visibility in all the models. However, the fall because of the finite size modeling of the environment, you can see some recurrences, and these recurrences lead to very counterintuitive effects. For example, in the case of amplitude damping channel and the depolarizing channel, you can obtain higher visibilities than you would expect in the case of without noise. So the green plot here, for example, is above the blue one, and similarly green and the yellow one here is above the blue one. For the Jaynes Cummings model, there is again some interesting cases, but the blue plot here is deformed because of the fact that it has H environment not equal to 0. And again, the interesting thing is that you can obtain higher visibilities than you would expect without the noise, even for the Jaynes Cummings. And clearly one sees that temperature also has an important effect here. The higher temperature leads to lower visibility in general. Now, given all that, what is the final figure of merit that one could arrive at? So the assumption that is made here is that you put these very vastly different experiments, their best results into the same envelope, which may not be possible, may be possible in future. And you take the best results, for example, the highest separation obtained, the longest time for of the spatial superposition obtained, sorry, and so on, and then go on to calculate the difference in visibility. So this, for example, has been done for the Jaynes Cummings model. And if one takes realistic temperatures that can be achieved in current fridges, that case is very near to the T is equals to 0 case that we described before. And one clearly sees that there is a difference in visibility while considering noise and that without noise. And this visibility can be quantified. And we have fixed the other parameters here. So it just as a function of proper time difference and calculated. So this difference is calculated at proper time difference of 1. So finally, conclusions. So the first conclusion, of course, is that noise on internal degree of freedom does affect the visibility. And we saw before that it could go either way. It could increase or decrease the visibility. So the noise model considered here is good in the way that locally acting environment also ascribes to time dilation. That is, the environment Hamiltonian or the noise Hamiltonian and the clock Hamiltonian are redshifted or they all experience time dilation in the time evolution operator. Visibility could also be more than that without the environment, which may be because of recurrence or maybe because of some other factors. Now, these visibilities have different susceptibility to lambda, the noise parameter, and this carries implications for actual experiments, which are modeled towards measuring the visibility and not towards phase estimation. So you could look up this archive link, and I hope that I will update this paper or the manuscript in like near future. Thank you.
Thank you very much, Harshit. So we have plenty of time for questions. If you want to ask a question, please put your hand up. I might start off. I was wondering about maybe you can keep sharing and just go back to
just a second.
Yep. So sort of in your summary slides, I think that was the next one. Sorry, the one about that showed back one, back another one, back one more. Yeah, this one. No. Yep. Slide 21, I think I want. Yeah. So the PD channel there seems quite unusual. As a function of the proper time difference, you seem to have a much stronger sensitivity, like the oscillations are going much more rapidly.
Yep.
So that seems like it would make it easier to detect a gravitational effect in this sense. Is that the right conclusion?
I think it would be helpful, as you're saying, that if the frequencies of this clock system are increased by some effect, maybe because of noise, then it would lead to better sensitivity. That is true.
Mm-hmm. Yeah, so that's quite an interesting effect.
Yeah, thank you for pointing that.
Okay, so any other questions? If you can't put your hand up, perhaps just indicate a thumbs up or something like that so I can see you. Still not seeing any other questions.
There's a hand up.
Ah, Sebastian.
Yep. Hi, hello. First of all, thank you for the nice talk. This might be a bit of a long shot, but I was wondering, are you familiar with the recent papers by Marios Christodoulou in Colorado Valley, where they proposed an experiment to actually test the discreteness of time in the lab, where instead of using interferometry and clocks, they're using quantum superpositions of two mesoscopic particles. Yeah, I was just wondering if you're familiar with that work, if you can maybe comment on the differences and compare them. If I understand correctly, with your approach, it's not possible to make a statement about the discreteness of time itself. Is that correct?
I think so. You're correct in this sense. So I guess my idea is that if you were to look at discreteness of time, you would have to look into some different experiments. This is just I don't know how to explain that result with this one. I'm not sure. So I've not followed that work, number one. Number two is that I'm not sure whether this work could be related to that. I'm sorry. Maybe I'll try to read that and follow up with you.
Yeah, that's fine. I'll send you the links in the private chat. I was just wondering if maybe you had heard of it and maybe there's ways to extend it, but I guess it's a bit of a long shot.
Okay.
But I'll send you the links and we can chat in private. Thank you.
Thank you.
Nick?
Hi. I was wondering, you show some results from your one-mode Jaynes Cummings model, and I was curious if you had any results for multiple modes in the Jaynes Cummings approach for the noise.
Not really. So the calculations that we have done are for a single mode case. And we were more interested in, for example, the temperature, the effects of temperature. So for that also we've resorted to single field mode and consider a Boltzmann distribution of the excitations. And then
so in this plot, the energy gap of your internal clock is 1, is that right? On the right plots?
On this plot. Yep.
Okay. Fair enough. Thank you.
Okay, any other questions? Okay, if not, then let's thank Harshit again.
Thank you very much.
Okay, so our next speaker is Daisuke Miki.
Yes.
So if you could share your screen, please. Great. Okay, that looks good. I can't hear you at the moment.
Can you hear? Can you see the pointer?
Okay, that's good.
Okay. Thank you.
Okay, so our next speaker is Daisuke Miki from Kyushu University in Japan, and he's going to talk about entanglement and decoherence due to gravity.
Okay, thank you very much for your kind introduction. My name is Daisuke Miki. I'm a master course student at Kyushu University. I thank the organizers for the opportunity to present my research at this conference. Today, I'm going to talk about entanglement and decoherence due to gravity for testing the quantum nature of gravity. This research is based on work with Akira Matsumura and Kazuhiro Yamamoto, which is published in PRD. My presentation is in 5 parts. First, I'll give a brief introduction to the test of the quantum nature of gravity and the role of entanglement. Next, I explain the system of our model. In the third part, I will discuss the evolution of the negativity to characterize entanglement and the decoherence behavior. After that, I'll focus on entanglement monogamy due to gravity. Finally, I'll finish with a brief conclusion. Now let's start with part 1, the introduction. The first is about a test of the quantum nature of gravity. Unification of general relativity and quantum mechanics is a challenging problem in physics. Many theories have been proposed, but there is no established theory. There are almost no experimental studies on quantum gravity. However, by the development of quantum technology, experiments to realize quantum state of mesoscopic systems have been proposed. And the superposition state of a mesoscopic particle might be realized in the future. For example, this figure shows such a proposal. In this proposal, using the Sterlinger-like experiment, a state of mesoscopic nanodiamond is split in a superposition state by an inhomogeneous magnetic field. If such a superposition of spatially localized state of a massive particles was realized, it can be used to test quantum nature of gravity. In this talk, consider a test for the quantum nature of gravity by assuming such an experimental proposal. The key is entanglement to verify the quantum nature of gravity. Entanglement is a non-local correlation, and an entangled state is written by this form. For example, we consider system A is entangled with a system B. Then, when we measure the state of system A, the state of system B is immediately collapsed. This is an interesting feature of entanglement. Moreover, entanglement is a quantum character. It is known that entanglement cannot be generated by local operations and classical communication, which is called LOCC, the theorem of quantum information. Local operation is an arbitrary quantum operation on only one subsystem, A or B. And an example of classical communication is sending the classical information from one to the other. This LOCC cannot generate entanglement, so a non-local quantum operation is necessary to generate entanglement. Using this property, we may say that if gravitational interaction generates entanglement, it means the quantum nature of gravity. Okay, now let us consider an example for testing the quantum nature of gravity by using a pair of particles. This test was originally proposed by both et al. And Marlet and Bedlar, and this is called the BMV experiment. For this experiment, we consider the following setup. First, we consider two particles with masses m1 and m2. separated by a distance d. Then, using the Stern-Gerlach experiment, we prepare each particle in a superposition of two localized states separated by a distance l. So originally, distance is d, superposition is distance is l. The initial state is given in this formula as a product of the superposition states. And then two particles interact by gravity depending on the distance. For example, when particle 1 is in the left side state, like this, and particle 2 is also in the left side state, the distance between these two particles is d, so the gravitational interaction is given by gm1, m2 over d, which gives unitary evolution. Similarly, the other cases are derived depending on the configuration of the position of the state. Here, they assume that the wave packet of each particle does not spread, so the states are spatially localized. The basis of the state is given by up 1, up 2, up 1, down 2, down 1, up 2, down 1, down 2. The quantum state of the two particles system evolves in different phases. This, and this. So the state evolves into the entangled state by gravity. In our work, we consider the configuration similar to the model proposed by Gwen and Ed Barnes. For this model, two particles are separated by a distance d, and the superposition is separated by a distance l. But unlike the previous model, the superposition is along the vertical direction of particle arrangement. When the system is prepared in this way, our distance between the same side particle, like this and this, the distance is d, and the distance between the opposite particle is the square root of d squared plus l squared. So the Hamiltonian is obtained by this form, by the basis of the past states like this. The Hamiltonian is simply calculated by this form and calculated in line 2, where sigma z is a Pauli matrix and I is the identity matrix. Here, the second term is a phase term of the total system, so does not affect the entanglement between the two particles. Therefore, only the first term affects the entanglement, and hence we regard H12 as the Hamiltonian of the total system. This model can be easily analyzed by using this Hamiltonian because of the symmetry of the configuration. And the system also evolves into an entangled state. Following the proposal in the BMV experiment, detection of the entanglement of the system will demonstrate the quantumness of gravity. I move on to part 2, model proposal. We generalize the previous analysis by Gwen and Barnes to the n-particle system. We assume n particles are arranged in a linear configuration separated by a distance d. And as shown in the figure, we assume that each particle is split in a superposition of two localized states separated by a distance l. And the superposition is along the vertical direction of a particle arrangement. We also assume that the initial state is simply by the product state of this form, and the particles are spatially localized during its evolution. Here, we focus on the entanglement between the first particle and the second particle. We are interested in how a quantum system coupled to the massive particles is influenced by gravitational interaction. In this model, two particles are entangled with other particles. So the entanglement between the two particles is affected by its gravitational interaction with other particles in the n-particle system. This may cause decoherence due to gravity. This will also a result of the quantum nature of gravity. Sorry, we discuss the dynamics of a gravity-induced entanglement between a specific pair for n-massive particles. The specific pair of particles are decoherent by the gravitational interaction with other particles. So we aim to investigate quantum nature of gravity by analyzing the entanglement and decoherence in the gravitating many-body system. Then we analyze the Hamiltonian of the n-particle system. For the two-particle system proposed by Gwen and Barnard, the Hamiltonian is given by this form. And the gravitational interaction depends on the distance between two particles. So the Hamiltonian for the n-particle system is simply obtained by extending the case of two particles. And this. Here Hij describes the Newtonian potential between the ice particle and the J's particle. And sigma z is a Pauli matrix and I is an identity matrix. We consider the quantum state of the system described by the density matrix rho to simply investigate the entanglement. Neglecting the decoherences due to other environments, we assume that the state evolves unitarily by the Hamiltonian and the density matrix is given by this form. Then we focus on the entanglement between the first and second particles. So we take a trace, we take a partial trace over the third particle to the nth particle in the density matrix. After a long calculation, we derive the reduced density matrix of the first and second particles exactly. Here the statistics represents a complex conjugation. Next with this slide, we explain how to find the evaluation of entanglement. We analyze entanglement using the positive partial transposition criterion. According to this criterion, the state is entangled if at least one of the eigenvalues of the partially transposed density matrix is negative. Here, the partial transposition is the operation of the transposition for only one subsystem. And then we introduce the negativity. Negativity N is defined as the sum of the negative eigenvalues of the partially transposed reduced density matrix rho 1 to pt. Then it can be shown that if the partially transposed reduced density matrix rho 1 to pt has negative eigenvalues, namely if the negativity is non-zero, the state is entangled. Next, I go on to part 3 of my presentation. Discuss the behavior of the entanglement due to gravity. First, this slide shows the evolution of the negativity for the two-particle system. This is the same model adapted in the previous research by Gwen and Barnes. The eigenvalues of partially transposed reduced density matrix are obtained by this, and the negativity evolves, and the negativity evolves as shown in this figure. The vertical axis is the negativity, and the horizontal axis is dimensionless time, normalized by delta 1, 2 over pi h bar. Here, delta 1, 2 is the gravitational interaction between the first and the second particles, given by this. This figure shows that in the two particles case, the negativity periodically oscillates between the maximally entangled and non-entangled state. The typical time scale of the time evolution is determined by delta 1, 2 over pi h bar, like this. Next, this slide shows a case for three-particle system. We can derive the negativity exactly from the reduced density matrix of the first and second particles. To simply investigate the entanglement, we here assume that the three particles have the same mass, so m1 equal m2 equal m3 equal m. The superposition distance L is equal to the distance between each particle d. By this assumption, the introduction between the first and second particles is equal to the interaction between the second and third particles. The left here, this shows the behavior of the four eigenvalues. The right here shows the behavior of the negativity as a function of delta 1 to t over pi h bar. The negativity is the sum of the negative eigenvalues. So the negative value in the left figure corresponds to the right figure negativity. Unlike the case for the two-particle system, the evolution of negativity as an estimator of the entanglement shows periodic modulation like this. This behavior comes from the gravitational interaction with the third particle. Therefore, since the additional third particle plays a role of the environment, the entanglement between the two particles is affected. Moreover, there are two periodic timescale behaviors of the negativity. One is this, and the other is this scale. The shorter period is determined by delta 1, 2, and the longer period is determined by delta 1, 3. This slide shows the case of the four particles. The left panel shows the evolution of the eigenvalues, and the right panel is the evolution of the negativity. Here we also assume that all the particles have the same mass and that L equals D. The state is entangled at an earlier time, and this region. But unlike the case for the two-particle system, three-particle system, there are regions without entanglement, like this region, and this, etc. Therefore, the two particles are more affected by the interaction with the additional fourth particle. The number of particles is further increases. This slide shows the eigenvalues and the negativity for the 10-particle system. The left panel shows the evolution of the eigenvalues, and the right panel is the negativity. One can see that the state is entangled only for a short period like this area. And the entanglement tends to disappear soon. This is understood as decoherence due to the gravitational interaction with other particles. We can estimate that the characteristic time of this type of decoherence is determined by delta 1,2 over pi h bar, and the order of h bar pi d over pi gm squared. We also examined how the decoherence behavior depends on the ratio of the parameter L over D. In the case when L is much smaller than D, and let me show the entanglement between the two particles is less likely to be affected by the other particles because the particles are far from each other. And the characteristic time is of the order of h bar pi d cubed over gm squared L squared. In the case when L is much larger than D, two particles rapidly decohere because the particles are close to one another, like this. The characteristic time is of the order of h bar pi d over gm squared. This is the same as the case for L equals D. Therefore, the decoherence time scale depends on the configuration and the scale of the superposition. We can examine the decoherence behavior analytically for the limit of the ratio L over D, and the number of particles n goes to infinity. Then we use the off-diagonal components in the density matrix. The off-diagonal components characterize the coherence of the two particles. So the decay time of the off-diagonal components determines that of the entanglement. The density matrix was derived by this form, and we evaluate the upper bounds of the off-diagonal components when n goes to infinity. Here, this inequality satisfies for an earlier time with which we estimate the decoherence timescale. So in the case when L is much larger than D, the upper bounds of the off-diagonal components are derived in this form. Since the off-diagonal components become zero when the two particles decohere, so the characteristic time of the decoherence is approximately h bar d over gm squared. In the case when L is much smaller than D, the upper bound are derived in the same way, and the characteristic decoherence time is approximately estimated as h bar d cubed over gm squared L squared. As a result, the decay time of the off-diagonal components in the reduced density matrix is estimated by this form, like this. On the other hand, the decoherence time for a 10-particle system is estimated by this form. And the decay time of the off-diagonal components explains the decoherence time scale for the 10-particle system numerically obtained. The decoherence time does not change so much even if the number of particles increases by more than 10. The system discussed so far can be simply generalized to a two-dimensional system. We consider the system consisting of L times L particles arranged on the xy plane, x-axis and y-axis. as illustrated in the left figure. Particles are placed at the lattice points, and the separation between the neighboring lattice point is d, like this. Then we assume each particle is in a superposition of localized states by a distance L along the direction of the z-axis. Z-axis is here. So superposition is like this. Here we focus on the entanglement between the two particles at the point 0, 0 and 1, 0, illustrated in red color. We determine the reduced density matrix of these two particles in a similar way to the one-dimensional case. And this slide shows the behavior of the negativity for 4 times 4 particles. Since the number of particles around the two particles increases, a significant decoherence effect is observed in comparison with that in the one-dimensional case. Next, I go on to part 4, and we focus on entanglement monogamy due to gravity. Here, we go back to the one-dimensional 3-particle system. In the previous section, we prepared each particle in a superposition state given by this. Here, we consider different initial state for the 3-particle system. The system consists of 3 particles, and the second particle and third particles are initially entangled, like this, but are not entangled with the first particle, the state given by this formula. The density matrix is derived by this form, like this. We analyze whether monogamy appears due to gravity by investigating the various entanglements in this 3-particle system. First, we regard the second and third particles as one system, like this. We analyze entanglement between the first particle and the system comprising the second and third particles. Negativity is derived by the partially transport density matrix and given by this form. Next, we analyze entanglement between the second and third particle, like this. Taking the partial trace of the density matrix over the first particle, the reduced density matrix of the second and third particle is derived by this form. The negativity is also derived by this. Similarly, we can analyze entanglement between the first and second particle, like this, and between the first and third particle, like this. But both negativities equal 0, so the first particle is not entangled with the second and third particles. As a result, the negativities are obtained by this form. It can be seen that the negativity between the first particle and the composite system of the second and the third particles, N1 to 3, increases. The negativity between the second and the third particles decreases, and vice versa. These properties can be considered as the effect of entanglement monogamy.
Just letting you know you've got 10 minutes left, including questions.
Yeah. Okay, conclusion. I'd like to finish by summarizing the main findings of our study. In this study, we investigate quantum memory body effect in the entanglement between a multi-particle system due to gravity. For the system with more than 3 particles, the entanglement tends to disappear through entanglement with other particles due to gravity. This can be regarded as a decoherence due to gravity in many body quantum gravitating systems. We estimate characteristic time of the decoherence. This depends on the ratio L over D. This decoherence time was obtained by observing the reduced density matrix when n goes to infinity. Finally, we discuss entanglement monogamy by considering the system wherein two out of the 3 particles in the system were prepared in an initially entangled state. That's all I have to say. Thank you for your attention.
Thank you very much.
Thank you.
So we have time for questions. Perhaps again, I'll start with one. So I probably just missed this, but can I just confirm? So when you show the particles, they are sitting in simple harmonic wells, are they? Is that the assumption that they're held in a simple harmonic oscillators, and that and then they're relaxing to their ground state under the influence of gravity? Is that the right picture?
Yes. Just wait.
Like I say, you probably said this, but I think I must have missed it.
This figure. Your question is the setup of our model, right?
Yes, the basic setup. I just
Yeah.
wasn't sure whether I'd got it right.
Yeah, we assume each particle is separated by this superposition. Each particle is prepared as a superposition separated by a distance L. And we assume that each particle, we assume that wave packets of each particle does not spread. So the particle's position is localized. And
I see. So they're they're classical particles sitting in flat space in superpositions of different positions, and then you're considering the gravitational interaction between them.
Yeah.
But is that right? But why don't they just stick together?
Stick together? So I can't follow your question. What do you mean?
So sorry, is there something holding them at positions so that they're d distance apart?
Yeah. The position is holding during the evolution. But
so they're in a harmonic potential, are they?
Harmonic potential.
Excuse me. I think that no harmonic potential, just free falling. Sorry.
Yeah, we assume that particles are localized positions, and
so they can't, under the influence of gravity, they can't move towards each other.
Yeah. So we consider only the gravitational interaction, and the position does not change during the evolution.
So you're just considering the effect on the superposition states.
Yeah,
So the entanglement occurs because of the different gravitational interaction depending on the
yeah.
superposition of positions.
Yeah.
Okay, I get it now. Sorry for that. Thanks for that
Sorry.
clarification.
Thank you.
We've got a question from Rob. Take it away, Rob.
Yeah, hi. Thanks. It's an interesting talk, but I guess I still don't quite understand the answer to Tim's question. So if you have these particles on a line, why don't they just and they're experiencing superposition due to gravity, why don't they accelerate toward each other under the influence of gravity? Like, what's stopping that, I think, is the question. And if it was answered, I didn't get it.
Your question is particles. Why particles are?
Well, the particles will attract each other under their own gravitational influence, so they'll accelerate toward each other, and yet they seem to be static. So why are they not accelerating toward each other? What is stopping that from happening is the question. At least it's my question. If it was answered, I didn't quite get it. I'm sorry.
Sorry, your question is 10 particle system?
Well, two particles.
Two particles, okay.
Like they're in superposition, but they will attract each other due to their own gravity. And why isn't that dealt with, or how is that dealt with? So the formula there, from what I can tell, assumes that the particles, like there's a force between them, but that force is not causing any acceleration. And so what stops that? Some other force must be operative to prevent that from happening. That's my question.
We consider interaction only by gravity, and this periodically oscillation is determined by unitary evolution, and these are behavior. Yeah.
But are the particles moving? It says they oscillate between the two states, but it looks like they're not actually physically moving. Is that correct, or did I misunderstand?
Yeah.
Like D and L seem to be time independent. But if that's true, they're not moving and they're not attracting each other.
Here we do not consider the particles, the distance D and L does not change here, we consider.
I think the assumption is that the particles are being, there's some trap that's holding the particles, localizing the particles.
Yeah, there's something pinning them down, basically.
Yeah, but there doesn't seem to be any description of what type of trap that is.
But the result assumes that D and L are constant throughout the problem.
Yeah,
is that correct? Okay.
Yes.
Right.
Okay.
Mm-hmm.
So that's not explained why, but that's the assumption.
Okay. Thanks. Any other questions? I don't see any other hands up, unless I've missed something. Okay, if there's no other questions, then let's thank the speaker again.
Thank you very much.
Okay, so I think the program calls for a 10-minute break now. So in the interests of not inconveniencing anyone who is just joining for the last talk, then we'll just wait 10 minutes before we start the next talk. Okay, so we're back again, and our next speaker is, is Akira Matsumura, who is also from Kyushu University. So Akira, can you share your screen, please?
Okay, can you hear me?
Yes.
Okay, just a moment. Can you hear my slide?
Yep, that's great. We can see your screen. Okay, so let's get underway. So as I said, our next speaker is Akira Matsumura from Kyushu University, and he's going to talk about gravity-induced entanglement in optomechanical systems.
Thank you for introduction. I'm Akira Matsumura from Kyushu University. I would like to thank the organizers for this opportunity to give a presentation. Today, I would like to talk about gravity-induced entanglement in optomechanical systems. This talk is based on this paper collaborated with Dr. Yamamoto from Kyushu University. Let's start. Our research is motivated by quantum gravity. Quantum gravity, which unifies quantum mechanics and general relativity, has been considered in various contexts. However, there are still no widely accepted theory and experimental evidences. Due to the circumstances, the question arises: gravity should be quantized? This question also includes whether non-relative gravity is described in quantum mechanics or not. This has not been verified yet. In this context, a test of quantum features of non-relative gravity by using quantum entanglement was proposed. Quantum entanglement is a non-local correlation known in quantum mechanics. A system AB is said to be entangled if its quantum state cannot be written in a product form. For example, if the spins AB are in the barrel state, they cannot be written in a product form. Such superposed states have the property that once the spin A is measured, then the state of the other spin B is collapsed into a corresponding spin state. In this sense, the two spins are correlated. There are two important properties of quantum entanglement. One is that quantum entanglement can be generated by the interaction given by Q number. The other is that quantum entanglement is not generated in classical processes such as local operations and classical communications, so-called LOCC. These properties give us one important consequence. Suppose two systems A and B and the gravitational interaction between them. If the gravitational interaction is described by Q number, then the quantum entanglement may be generated between the two systems. Quantum entanglement due to gravity means that the gravitational interaction cannot be described by LOCC. In this sense, gravity-induced entanglement can be a witness of quantum features of gravity. This is the basic idea to test quantum features of gravity by using entanglement. In the following, I would like to review the proposal using two matter wave interferometers to test gravity-induced entanglement. In this proposal, we prepare two spin particles. Each particle in the interferometer is superposed by a non-uniform magnetic field. The particles are coupled with each other by the gravitational interaction. After traveling time, we use the magnetic field to bring the particles together at a certain position. Then we measure the spin correlations of the particles. If there are no gravitational interactions, each particle would evolve independently in its own interferometer. What we are interested in is whether quantum entanglement between the spin particles is generated by the gravitational interaction. I would like to briefly present some calculations on this proposal. To understand how gravity-induced entanglement is generated, at first, let me introduce the case where quantum entanglement is not generated. We consider that the spin particle in the green part is initially in the superposition of up and down spins. and the particle in the blue part is in the up spin state. In the first stage, a non-uniform magnetic field is applied, and then the particle in the green part will be spatially superposed. On the other hand, the particle in the blue part does not form a superposition. The state of the particles are given in this equation, where the states Li and Ri are defined by these equations. For example, the state L1 represents that the particles in the green part is in the upper spin state and moves on the left. On the other hand, the state R1 indicates that the particle in the green part is in the down spin state and moves on the right path. During this experiment, we assumed that each wave packet of particles does not spread. In the second stage, the phases of the state are rotated by the gravitational potential. Depending on the distance between the particles, the different phase shifts induced. The phase phi L is determined by the distance between the position x1L and x2L. And the phase phi RL is given by the distance between the position x1R and x2L. In the last stage, the magnetic field is applied to bring the particles back to their original positions. Then the two particles are localized at x1c and x2c, and their spins in this state with the non-trivial phases. However, it is easy to find that the spin state of the second particle is factorized, and the state of the particles can be written in a product form. Hence, there is no generation of entanglement in this case. Let us move on the case where the quantum entanglement is generated by the gravity. In contrast to the previous case, we consider that both of the particles are initially in the superposition of the up and down spins, like this. In the first stage, by a non-uniform magnetic field, the particle in the green part will be in the superposition of two particles. Unlike the previous case, the particle in the blue part also will be in the superposition of two particles. The state of the particles after the first stage are given in this equation. The state of the particle in the blue part is the superposition of two localized states, L2 and R2. In the second stage, similar to the previous case, the phases of the state are rotated by the gravitational interaction. However, in this case, there are 4 different phase shifts depending on the distance between the particles. The another phases phi LR and phi RR are determined by the distance between the particle in the green part and the particle at x2L in the blue part. Finally, we apply a magnetic field to bring the particles back to their original positions. The states representing the local position of those particles are factorized, and then we find the superposed state of the part spins, which is different from that in the previous case. The resulting spin state is entangled. For example, let us consider that the phase phi RL given by the shortest distance is dominated. In this case, the other phase is phi IL, phi LR, phi RR neglected, and the spin state is approximated as follows. This state cannot be written in a product form when the phase phi RL is not 2n pi, where n is a natural number. Hence, we find the state is entangled. The important point is the time evolution in the second stage. Since the gravitational interaction is represented by a Q number, the phase shift due to gravity take different values associated with localized state of the particles. This is how gravity generates quantum entanglement between the two superposed particles. From now, I would like to introduce our research. We consider another proposal to test quantum gravity-induced entanglement using not matter wave interference but optomechanical systems. This part of the figure shows an optomechanical system. The optomechanical system is a quantum system consisting of a cavity photon and an oscillating mirror. The mirror behaves as a quantum oscillator, and which is a part of the cavity and coupled with the cavity photon by radiation pressure. The basic idea is the same. We prepare another optomechanical system and consider the gravitational interaction between the oscillating mirrors. In this system, gravity-induced entanglement is generated between the oscillators. Also, the photons in separated cavities are entangled by gravity through the photon-oscillator interaction. There are some previous studies about gravity-induced entanglement in optomechanical systems. This work performed the perturbative analysis of the couplings between the photons and the oscillators. This another work considered the linearized Hamiltonian with respect to the photon-oscillator interaction. On the other hand, we address non-perturbative and nonlinear analysis to discuss the gravity-induced entanglement. In particular, we revealed the generation mechanism of gravity-induced entanglement of photons. We also consider the effect of decoherence for photons and compare the entangling time with the decoherence time. This is the experimental setting assumed in our paper. This part corresponds to one of the optomechanical systems. This is the suspended torsion pendulum with two mirrors at each end, which correspond to the oscillating mirrors. We prepare another optomechanical system and consider gravitational interactions among the oscillating mirrors. We discussed this model in our paper, but in this talk, I will use a simple model to explain the mechanism of gravity-induced entanglement. This is the simple model of the optomechanical systems. This is one of the optomechanical systems. A photon comes from a source and it is divided into two passes by a half mirror. In this pass, the photon just enters the cavity, while in the other pass, the photon enters another cavity and then it is coupled to the oscillating mirror. We prepare another similar optomechanical system and consider the gravitational interaction between the oscillating mirrors. Without the gravitational interaction, the green and blue parts of the system are independent. So there are no correlations such as quantum entanglement. We want to investigate how the gravitational interaction generates quantum entanglement between the green and blue parts. To discuss it, we will present the Hamiltonian of the total system. Let us first consider the interaction between oscillator and photon. This figure shows the gray part of the total system. The cavity is constructed by two mirrors, where one is fixed at XL and the other at XL is connected by a spring. The frequency of the photon in the cavity has discrete values given by this equation, where c is the light velocity and L is the length of the cavity. Since the spring is attached to the mirror oscillates and the length of the cavity varies. Then the resonance frequency of the photon changes by the variation of the cavity length. Assuming that the amplitude of the oscillator is small, the frequency of the photon is approximated as this form. Due to the variation of the resonance frequency, the Hamiltonian of the photon in the cavity changes. When the oscillation is small, the Hamiltonian is approximated as this form. This second term corresponds to the interaction between the photon and the oscillator. The Hamiltonian of this optometric system is composed of the three parts: the free Hamiltonian of the cavity photon, the Hamiltonian of the oscillator, and the interaction between the photon and the oscillator. Next, we consider the gravitational interaction. This figure shows the purple part of the total system. The position of each oscillator in the x direction are denoted by xa and xb, respectively. The distance between the two oscillators in the y direction is h. The Newtonian potential is given by this form, where m and mb are the masses of the oscillators. Assuming that the oscillations are small, we obtain the approximate form of the Newtonian potential up to the quadratic order of the positions of oscillators. Under this approximation, gravity just creates a law of the spring. The cross term appearing here corresponds to the interaction between the oscillators. This term induces quantum entanglement between the oscillator. The Hamiltonian of the total system has the 7 parts. Each part is given as follows. HA and HB are the Hamiltonians of each oscillator, where Q and P are the dimensional position, the momentum, and omega A and omega B are the frequencies of the oscillators. HAB corresponds to the interaction by the gravity between the oscillators. Roughly speaking, the coupling constant gamma is determined by the Newtonian constant. HC and HD are the free Hamiltonian of the photons in the 4 cavities, where omega C and omega D are the frequency of the photon. HC1 and HBD1 correspond to the photon oscillator interaction of each optometric system. The photon oscillator couplings are characterized by the parameters lambda A and lambda B. We discussed the dynamics of this system in a non-perturbatory and nonlinear way. The interaction between the photon and the oscillator is given by the third order of the variables. It seems to be difficult to solve the Schrödinger equation. However, it is important to note that the photon number is conserved under this interaction. This is because the photon is just reflected by the mirrors, so there are no losses of photons. Hence, the Hamiltonian is diagonalized under photon number states. Given photon number states, the total Hamiltonian acts like this, where EPH is the energy of the photon and in the cavities, and N and N prime. M and N prime are the number of the photons in the 4 cavities. What we have to do is to diagonalize the remaining operators for the oscillators to solve the Schrödinger equation. Here, let us remind that the Hamiltonian of harmonic oscillator, HA and HB, and the gravitational interaction, HAB, are given by the quadratic form of the oscillators. Also, the terms which come from the photon oscillator interaction are given in the linear form of the oscillators. because the photon number operator is diagonalized. The part of the quantum operators appearing in this equation is at most quadratic order of the oscillators. Hence, we can solve the Schrödinger equation of the total system. We prepare the initial state and solve the dynamics and investigate the quantum entanglement. The initial state of the green part is given as follows. We assume that a single photon is emitted from the source, and the single photon passes through a half mirror, and it is in a superposition of two passes. The single photon enters the cavities and forms the superposition of states that the photon is in the cavity C2 and C1. The initial state of the oscillator is assumed to be a ground state. We consider the similar state for the blue part. We investigated how quantum entanglement arises between the photons in the green and blue parts. To quantify the entanglement, we use the negativity, which is defined by this equation. It is known that if the negativity takes a non-zero value, then the state is entangled. The negativity of the photons obtained from the solution of the Schrödinger equation behaves like this. The horizontal axis is time, and the vertical axis is the negativity. The negativity periodically changes and takes a maximum 0.5. Since we solved the dynamics exactly, the time scale to reach this maximum can be found analytically, which is given by the following formula, where gamma, lambda A, and lambda B correspond to the relation coupling and couplings of the photon and the oscillator, respectively. So this formula means that the smaller couplings lead to the longer time for generation of entanglement. Let me explain the mechanism of entanglement generation. If the system is considered, there is the effective interaction between the photons due to gravity. To clarify it, we focus on the pink part of the total system. The interaction is given by the effective interaction is given by the following process. First, the photon D1 pushes the oscillator B by radiation pressure. Then the spring given by the gravity is stretched. The stretched spring pulls the other oscillator A at a separated position. This leads to the small variation delta of the cavity length of the photon C1. With the small variation, the resonant frequency of the photon C1 changes, and the Hamiltonian of the photon C1 varies like this. The variation of the Hamiltonian delta H is given by the variation of the cavity length delta. Let me explain how delta is estimated. The large displacement of the oscillator B by radiation pressure of D1 leads to a large delta. And then when the spinning constant due to gravity is large, the position of the oscillator A is shifted well by the spring of the gravity. On the other hand, when the spring constant of the oscillator A, this part is large, the position of the oscillator A is shifted well by its own spring. On the other hand, when the spin constant of the oscillator A is large, the destroying force acts well, and the cavity length does not change so much. Hence, the variation delta is roughly given by this equation. The first question is the ratio of the two spring constants, and the second part is the displacement of the oscillator B by the radiation pressure of the photons D1, which is proportional to the number of the photons D1. Expressing the small variation delta by the parameters in our model, we find that delta H is given in this form. This is the effective interaction between the photons, whose coupling is given by the inverse of the entangling time. Also, we can check the generation of maximum entanglement. Under the evolution given by the small variation of the Hamiltonian delta H, the state of photons achieves a maximum entangled state when the negativity takes a maximum. Finally, let us consider the quantum decoherence of photon. Here, we consider photon leakage as the mechanism of decoherence. The photon leakage is described by this interaction between the photon C in the cavity and the field B in the external system. By this interaction, a state with one photon and the vacuum of the external field becomes a state with zero photons and the excited field. Under this interaction, the following Hilbert equation is obtained by performing the Markov and the rotating wave and the Neumann approximations. The first term is the von Neumann equation given by the Hamiltonian of our model. And the second and third terms correspond to the non-unitary part, which represents the photon leakage and amplitude damping. Under this time evolution, the negativity between the photons is calculated like this, where kappa C is the dissipation rate appearing in the non-unitary part. This formula shows that the negativity is very small when the photons are dissipated. Let us compare the decoherence time with the entangling time of the photons. If the entangling time is shorter than the decoherence time, the quantum entanglement is sufficiently generated. The required condition is given in this inequality. To discuss how this condition is realized in a realistic setup, we use the usual parameters of experiment without gravitational interactions. For such parameters, the inequality is given in this form, where the capital omega A and omega B are the frequencies of oscillators determined by only the spring attached to the mirrors. The capital A, lambda A and lambda B are the original optometric couplings without gravity. G and GB are the parameters characterizing the gravitational coupling. The couplings appearing in the right-hand side of this condition are typically small. Evaluating these couplings as 0.1, which is very large estimate, the right-hand side is given by around 10 to minus 3. According to this review paper, the value realized in the present experiments is 10 to minus 2. Hence, this has not been reached yet in the present experiment. It seems to be difficult for the detection of quantum entanglement due to gravity. Okay, let us summarize my talk. We investigated gravity-induced entanglement in optomechanical systems. We solved the nonlinear dynamics non-perturbably by using the conservation law of the photons. We found the generation of maximum entanglement photon and clarified its generation mechanism. From the comparison with decoherence time, we give the condition for the dissipation rate to generate the entanglement sufficiently. That is, thank you for attention.
Thank you very much, Akira.
Thank you.
Okay, so the floor is open for questions, and Rob is the first cab off the rank.
Yeah, okay, thanks. That's an interesting talk.
Thank you.
You did partly address at the end some of my concerns about noise, but this is a rather general question, and I don't know how silly it is. So we're trying to see if the two cavity systems can become entangled due to gravitational attraction of the oscillators, right? If you go to those two L-shaped things, right? Maybe back a slide or two. Yeah, well, this one would be fine. So the point, well, no, backwards.
Sorry. No.
Yeah, this would be fine here, or that one. Yeah, that's fine. So,
Okay.
so of course, what I'm wondering is, has anybody given thought to seeing if one can entangle these things when we use some other interaction? So for example, suppose we have these oscillating springs and they're magnetized. They would attract each other magnetically, or there's a tiny charge on each of them. And I know to test gravity, we want, of course, to get rid of all of that. But what I'm wondering is, has anybody done an experiment or given thought to the analysis of doing exactly this experiment, but some other interaction between the two oscillators induces negativity? I'm just wondering if we understand that well enough so that we know how to isolate these things to test gravity, if that makes any sense. Because like electromagnetism, some electromagnetic interaction between those two oscillators presumably will induce entanglement for the same reasons.
Yes, yeah.
Right? Has anybody, I'm just wondering if anybody's ever thought about that or done an experiment? Like, we're trying to do the hardest experiment first. Why not do the easier one?
Yeah, so yes, I think that it is easy to find the negativity by electromagnetism in the experiment. So the gravitation, however, the gravitational interaction is so weak. So that is
well,
so that, yes. Sorry.
Yeah,
yes,
I know
so
that, but the point is, can we be sure for this complicated setup that electromagnetism will induce negativity the way we understand it, right? It's sort of the control force. And I guess I would think if we could induce it in a way we understand very well with electromagnetism, then it would give me greater confidence that when we isolate all other forces except gravity, that it would do it there too. Like I know there are lots of stray things, but has anybody ever entangled two cavities like this at all using some mechanism is my question.
Sorry, I don't understand well, but so
maybe somebody else does.
So if there are any other interactions, so we need to distinguish the source of the entanglement, right? Okay. So we need the analysis of the generation rate of the other interactions to
That's
distinguish
right.
To distinguish.
And I'm wondering if anybody's. So I'm wondering if anybody has ever actually done that and then done the experiment to demonstrate we understand everything about that. So I agree with you. That's what should be done. And it just occurred to me when you were talking, has anybody ever actually looked at this?
Maybe I can ask a question and just comment on Rob's question.
Thank you.
So just to comment first, I imagine nobody's done exactly this experiment with an electromagnetic force between them.
Yes.
But I think there definitely are examples of experiments where you entangle quantum particles using the electromagnetic force, in which you can describe it as a Q number, so to speak, in terms of the force. But I guess the difference is that there we understand that at some fundamental level, it's photons being exchanged between the objects that leads to the entanglement. Whilst here it's not so clear if such objects exist for gravity, as in gravitons. Is that kind of, I'm not sure.
Well, if I could comment on the comment, yeah, I agree. We understand that electromagnetism does it elsewhere, but should we not understand exactly how it would work for this particular setup? Maybe there's something we're missing, right? It's a complicated setup. So the idea is not to see if electromagnetism would entangle. We know it does. The idea is to see how it would for this particular experiment to be sure we have that under control.
Mm-hmm. Yep, interesting.
That's all I'm trying to point out.
Yeah.
Thank you.
So Akira, my actual question was,
Yes.
So you described everything in this simplified version,
Yes.
but you skipped over an earlier, more complicated setup. I wonder if you could just say a few words about that setup and why that is more like what you would, I'm assuming this setup is the one that you would sort of be thinking of actually trying to build in the lab.
So yeah, so so sorry, I don't understand you good.
So my question is, what are the special features of this setup?
Okay, okay, thank you. But I think this setup is the free from the Earth gravity, right? So this is the suspended torsion pendulum. So this in this setup, the Earth's gravity is cancelled out, and in this setup, the gravitational interaction between the oscillators. So sorry, how to say. So in this setup, we can focus on the focus on only the gravitational interaction between the oscillators, and from any other from the Earth gravities, right? So
Okay.
yes, that I think just that is the advantage of this setup.
Okay, good.
Thank you.
Do we have any other questions? I don't see any. Oh, yep, there's a hand up. Show.
Thank you for the talk. This is probably a very stupid question, but how feasible is it to characterize the position of a mirror, like a mirror that actually reflects, works as a mirror with a Q number? Like, I presume there would be gravitational interaction with other, the rod, whatever, and there's all these other interactions, and it would be hard to characterize the position of a mirror with a Q number. I would presume it would decohere. There would be other decoherence effect apart from the emission of the photon out of the cavity. And I was just wondering how. Is it possible to describe the position of the mirror as a Q number, or yeah?
Oh, so okay. So in the present experiment setup, the mirror can be quantum system in the sufficient cooling case, right? Then we can use the quantum reasoning of the mirror's central position, central motion. Is it clear? So I don't understand your question.
Like, this is probably very stupid, but like describing the position of the mirror in as a Q number, is that already done in an experiment or?
Yes, but if there are any decoherence effects, so we can so the mirror position is classical, I think. But in this case, we consider the ideal system free from the decoherence effect on the mirror.
Yes, but like I guess the first step we require to do this experiment would be like the ability to describe the mirror as a Q number. Do you know if that's feasible in an experiment, or we're still quite far from that?
I think the mirror is quantized here, Sho.
Yeah, I know it's quantized in theory, but is that possible in an experiment? Like how close, or we've already done an experiment when the position of the mirror is quantized in an experiment, or
yes.
So sorry, I don't understand your question.
I think Kim answers the question.
Yeah. Okay.
Okay, so I think we're basically out of time now.
Sorry, thank you.
So let's thank Akira again for a very interesting talk.
Thank you very much.
Okay, so that's the end of our session this week. The next Australian session will be held on the 18th of February, and Nick will be hosting that one. So look
That's
forward
the night
to
of the 17th. That's the night of the 17th in Waterloo.
yes, for the correct. Looking forward to seeing you all then.
Right.
Thanks again.